Welcome back to the classroom. My name is Mr. Wong. Today we're going to be covering the 2019 HSC Physics paper, question 35. This is to cover Module 5, Inquiry Question 2. So in this question, we have the apparatus shown. I'll screen it out. Is attached horizontally to the roof inside a stationary car, as you can see here. The plane of the protractor is perpendicular to the sides of the car. So you can see perpendicular to the sides. So you can imagine our car looks like this, or our car kind of looks like this, and we're looking towards the front of the car. So you can imagine we're at the back and we're looking forwards, or if we want to draw a side-on view, the car is moving in this direction and we are looking out this way. So we see a pendulum, we see a protractor. What's the question asking us? It says the car has then driven at a constant speed on a horizontal surface, causing the string to swing to right or to the right. So our pendulum will now move towards this direction here and remain at a constant angle. Okay, measured with respect to the vertical. So angle theta, like so. In your answer, derive an expression that relates a feature of the car's motion. So this is just a feature you could talk about. So there must be multiple options, but you only need to pick one. Okay. So what do we have here? Well, we know that if a pendulum is creating this particular angle, all right, we know that the car is moving at a constant speed. Okay. However, if you recall from our ideas of frames of reference, if you're traveling at a constant speed, you shouldn't be able to tell if you're moving at a constant speed. Okay, so, or tell your directional orientation and all that. So if I'm moving at a constant speed, but the pendulum is swinging like so, then I should be able to tell that the car is, in this case, turning towards the left-hand side, right? So there must be some kind of acceleration going on. So the only scenario where we can have a constant speed, yet still have some kind of acceleration, is if we're undergoing some kind of uniform circular motion. Okay, so what we can say firstly is the car is undergoing uniform circular motion. And is accelerating towards the left. So uniform circular motion, just write that down here, uniform circular motion with a centripetal acceleration towards the left. The reason being is because we can see that the pendulum is swinging right. So you can write as pendulum swings towards the right. Okay, so if our car is undergoing uniform circular motion, then we can equate its motion with centripetal force. We can also equate our own vector diagrams of this pendulum here, right? So for centripetal force, we have mass, we have velocity square, we have R. Okay, so there's a couple of features you could talk about. You could talk about the radius in which the car is going at in its circular motion, or it could be the velocity. You might even want to find the centripetal acceleration. So there's all these different considerations that you can look into. Okay, so to the right, what we could say is if our car is traveling at a really high velocity, assuming that centripetal force stays constant and mass of the car is constant, then the velocity and the radius in which the car undergoes that circular motion would be directly proportional to each other. Okay, so as the car, so as such, the pendulum can be used to calculate the circular motion or the radius of the car's circular motion. Now, some people might be thinking, how can we use a pendulum up here to work out if the car, how far is the car rotating in its particular radius? Well, see, the thing is, we have centripetal force pulling this in, and that should be equivalent to the amount of centripetal force felt by our pendulum as well. Okay, so the tension on the string is pulling in a way that it cancels out the weight force, but there should be enough, but the horizontal component of the tension force should reveal the similar amount of centripetal force this car is experiencing as it is rotating towards the center. Although I say experiencing centripetal force, we do know that centripetal force is a net equivalent force, so just keep that in mind. Okay, so just write that formula there. Now we can try and work out some, explanations to that. Okay, so the radius of the car's motion, the higher the velocity, the higher the radius. As we said, because V is directly proportional to R. Now, when we draw out the motion, this is what we get. We get theta. This is our pendulum there. We have the weight force pulling it down. We have the tension force. We know that the thing that actually affects its centripetal motion is the horizontal component of our tension force here. So this horizontal component like so. So let's have a look at what we can say. So the horizontal tension force will be the reason for our centripetal force, which is also mv squared r. If I want to try and find the component of this tension force here, I can simply use my gravitational force. So here we have a tan theta relationship where tension force horizontal is at the top and G force at the bottom. Again, this is also our net force, so you could write net force as well. It would mean the same thing. And so that this formula would look something along the lines of tan theta. It's quite a messy one, this one, I must say. So mg tan theta equals to mv squared over r. If we want to make r the subject of the equation, we most certainly can. I will just try and see if we can change the color. Unfortunately, with this recording here, there's a little bit of an issue where there's blinking going on when I record with the normal colors, so you'll just have to deal with these more fancy ones. So the m's cancel each other out. We have g, acceleration due to gravity, tan theta. So you could even, move tan theta over and work out what's the acceleration due to gravity, or you could say this relationship that we have here can represent the acceleration of the car, or you can work out the velocity of the car as well. This one we'll just look at the radius, okay? So if we want to make radius the subject of the equation, r is equal to, let's see, v squared g tan theta. And so that's the radius of the circular motion. Technically uniform circular motion, but since we're gonna run out of space, I'm gonna write that. So that's the one there, okay? Now here's a little bonus. Let's say if we want to find the velocity, okay? So from the original equation that we had, g tan theta equals to v squared over r. So if we move everything over, v equals to the square root rg tan theta. This is the what we can call design speed, but we can also interpret this as the speed in which the object is moving in its tangential velocity or tangential speed. And that can also give us some details about the car's motion as well. Okay, so this is the final response. The car was driven at a constant velocity, but we know that it's undergoing centripetal acceleration towards the left because the pendulum is swinging towards the right. As such, we know that there must be a net resultant force, which we also call it the centripetal force, and that the tangential velocity is directly proportional to the radius. So once the tangential velocity increases, the radius of the car as it undergoes that uniform circular motion will also increase. That concludes the explanation for this particular lesson or this particular exam question. If you found it useful, give it a like, subscribe, and I will see you next time. Thank you for joining.